Hello, everyone. So, in the first lecture I gave you guys, I said I wanted to talk about what happens in a fluid when you exert or subject it to some sort of force, and that force is acting much faster than the speed of sound in that fluid medium. So, the idea is you have like some water here, you got like a little spoon in the water, and the force would be something like this spoon driving it. And the rate at which the spoon is moving back and forth, let's say it's just like some harmonic oscillator, and we'll say it's just the same motion over and over again. The motion's pretty slow. This would be a faster motion. Let me move away so I don't destroy my computer. It would be a faster motion, much faster. So that's what I mean by that time scale of the external force on the fluid, right? So the actual speed of sound within the fluid is fixed, but the speed at which I exert some sort of force that acts on the fluid is what we're varying here. So the case in which that time scale of force is like very, very slow compared to the speed of sound in that medium is what we usually see in everyday life. Imagine a stream flowing over a rock. The stream is hitting the rock and the rock is perturbing the water a lot slower than it takes for those perturbations to spread throughout the water in the stream itself. So what if I were to move the spoon really, really fast, like near the speed of sound of water, which is about 100 meters per second? Or in air, what if a plane flew really, really fast, like faster than the speed of sound? That's the question. That's the sort of phenomenon that I wanted to talk about. But before we talk about that, we have to have a language of fluid mechanics. Fluid mechanics has some assumptions. Even in Newtonian physics, when you're dealing with just one particle, you have to understand the language, right? If I say F equals ma, you say, well, what is a force? What is acceleration? What is mass? What are any of these things? Well, they're specific mathematical constructs called vectors. And a point is a very big idealization. I have to explain what that means, etc. You have to do the same thing for fluid mechanics. So starting from the ideas of points, and I think I am just going to test my marker real fast. Beautiful. So starting from this idea of points, you have this point mass, and you can exert a force on it, and it makes it do stuff. So in fluid mechanics, we're going to take like a lot of these points. We know water is ultimately made up of molecules, so we aren't actually going to deal with the molecules themselves, like in Newtonian mechanics. In Newtonian mechanics, we say we have like a particle, and we say like it's in gravity or something, and we're like, what does it do? In fluid mechanics, we're going to be doing that too, essentially. And interestingly, the laws of physics are not changing. So Newton's laws of physics are still the governing equations here. The difference is the mathematical construct is not a point, but a parcel of fluid. So we're going to pretend that there are really no molecules in a sense. What we're going to do is we're going to say, let me scroll up to find some white space here. Yeah, okay. So we have like a glass of water, and we're going to divide that water into like little cubes. And within each one of those cubes, there's like n molecules, where n is like a huge, huge number. And what we're going to say is that we're going to average the speed of those molecules, and we're going to average the density of a region of those molecules. You can't define density with just one molecule, but you can define it over a small number of molecules, the density of those molecules. So each one of these little squares that we're dividing the molecules up into is what I'm going to call a parcel of fluid. Let's call it a volume for V. And within V, there's only one of these values. So we're going to choose these boxes very carefully such that the velocity and the density of the entire box is pretty much uniform. So you want to consider some scales here. You want to consider the mean free path of a molecule. How far does a molecule travel before it collides with another molecule? If you're picking too small a box and the molecules don't have time to collide, they're all moving at very, very different velocities. So I want to smooth that velocity out a little bit, make it a little more mesoscopic. So I want to choose a box bigger than the mean free path so that these molecules are colliding, and I can actually define a coherent velocity field that makes sense for that whole parcel. Because if these molecules are moving 1,000,000 meters per second and these are moving 1 meters per second, how can I assign one velocity to that box? So there's a couple of other scales we want to consider, but at the end of the day, the thing is we just want these to be singly defined for the entire box. So we choose the boxes that way, and that's called the continuum hypothesis. He talks about that down here. He says essentially what I said, but he doesn't talk about why and how we choose the boxes to be the size that they are. This is essentially sort of you would call it a tautology in philosophy or debate. In physics, we like to call it a self-consistency assumption. That is, we assume these idealizations that we want, and then we ask what are the conditions necessary to achieve those idealizations. So we say we want a field here, and oh, sorry, I forgot to connect a dot. So we do this thing with the parcels, right? And then each one of these parcels is going to correspond to a single point in space. That's very key to understand. So now that we have that, every single point in space has one of these. Every single x, this is xyz. This is a vector. So every point in space has two fields associated to it. A density field, which is a scalar field. It tells us at this point in space, this is really dense. At this point over here in space, it's still not so dense. There's not so many molecules in here. And the velocity is theoretically the entire parcel of fluid moves with this velocity. That's the idea. In reality, it's kind of an average over what the molecules are actually doing. And we kind of average out the idea of these individual molecules moving, and we concentrate on just like, say, a little box of water moving. So you got like a little box of water moving around instead of like in the box of the molecules, what they're individually doing. So every single point in space now will have a u associated to it, a velocity, and it will also have a density. And those are the only two quantities that we're interested in these kinds of fields. If you guys know a little bit of physics, you know about the electrical field and the magnetic field. This is a similar mathematical construction. It's not physically similar. Although actually interesting to see, this is quite similar. In viscous, incompressible flows are actually at the same math as magnetic fields. But put that out of your mind physically, but mathematically it's the same. At each point in space, we have an electric field, right? It's the same thing with this, except there's two fields now. There you go. That's the continuum hypothesis. Now that we have that, right. So he's talking about how we kind of ignore the molecules and kind of, average them out. But when we get down to the actual equations, you'll notice that there are some things that pop up in there. This is just kinematics of fluid mechanics. I don't see you, pressure, and I don't see you, viscosity. Where are you? Okay, viscosity and pressure might be a little bit later. But the point is, you will have an equation like that equation there, and that'll essentially be like the Newton's laws of fluid mechanics. But you'll see these little constants in here. They're not here yet, but you'll see a constant for like viscosity, right? Which is like how sticky something is. Honey is really viscous. Water is not so viscous. You'll see pressure. And that's actually a very sneaky way for us to continue to consider the individual molecular motions while actually not really considering them. So these things, these fields, the velocity and density, they imagine there are no molecules. But the motion of the molecule still sneakily kind of shows up in the equations anyway, because of course they have to, in terms of temperature, in terms of viscosity. So we kind of sneak them in there and idealize them into kind of these constants. So that's essentially where they go. So bear in mind, he doesn't really say this, but that is kind of a sneaky sweeping of under the rug in fluid mechanics, is that we aren't really ignoring the molecular motions. We're simply simplifying them into these kind of constants that show up. So what do we got? Wait. So we ignore the vast majority of the ocean temperature is constituents, blah, blah, blah. Does he say what I just said? Let's see. That's of course grained. The underlying particles in the direction. The internal motions that don't show up in the he does. Okay, he does say it. Temperature of the fluids, another field. Okay. Yes. Also the viscosity. Both of those things. So temperature is, give or take. Lighting is so fucking weird. Sorry, I'm filming this pretty late at night. I was climbing all day, so the lighting is really bizarre. Okay. So temperature is roughly like the average kinetic energy. It's the average of the velocity squared. So this is an average, it's a mean, right? The arithmetic mean. That's what's known as a first moment, more generally in statistics. If you go further into like variation and stuff, there's something called a second moment as well. So the first moment is just kind of the average velocity. I have a bunch of molecules, they all have different velocities, and I want to average those velocities. I want to say what the average velocity is of all of them. First moment, that shows up as temperature. Viscosity shows up as what's known as a second moment. Pressure also is a second moment. So pressure is a second moment. Xi, second moment. So pressure is that I there, fix it to X. Now we're talking about the velocity in the X direction. If you change the I to Y or Z, you're talking about velocity in the X or Z, the Y or Z direction. Start with X here. So you have a bunch of molecules. They can move in three-dimensional space. We're interested only in their X velocity for now. Set I to X. Now, what we're wondering is two different molecules at two different locations. how correlated are their x velocities? That is, if I'm all the way over here and I'm all the way over here, is there a correlation between the velocities of these particles? That's pressure. That's like an outward, isotropic outward force, or inwards. Well, no, it's never inwards, but negative pressure can be. Imagine it only positive for now. It's only going to show up as positive. And then there's another quantity called viscosity. Viscosity is also a second moment, but it's a shear correlation between these two things. That is xi, xj. So the idea is if I have a molecule here and a molecule here, how is the y velocity of this guy correlated with the x velocity of this guy? And that macroscopically, that shows up as stickiness, a resistance to flow, a resistance to shape change. You have honey, you put a drop, and it goes like, bleh. You have water, it just instantly goes that. The more viscous, the more resistant it is to shape change. So the point being here is what he does touch on it, is that where the molecules aren't actually going away, they're being simplified, and they show up whenever you see temperature, pressure, viscosity in an equation. That is the individual molecules that we kind of swept under the rug, coming back to say, no, we do have relevant physics that you have to talk about. So, right. So there are two different ways to think about a position in space in fluid mechanics. Time is time is time is time. But in terms of space, we have like this water here, right? And let's say the water's kind of flowing. Think about a stream. So there's two ways to think about this. One, you can think about yourself in a boat kind of going along with the stream. That's the one that's called a Lagrangian description. Then there is, say you're a rock in that stream and the water's flowing and you're standing still. That is called the Eulerian or Eulerian, however you like your Greek pronunciations. That's the Eulerian description. There's no canonical choice. It's whatever makes the physics more evident. So we'll switch between them freely because some work to determine certain physics and some work better to determine other physics. Yeah, path lines and streamlines. So essentially, a path line, I think a path line is over space and a streamline is over time. Yeah, so essentially, if you have this velocity field, this thing u, and at every point in space, this is a point in space right here, and at every time, that defines a velocity. So you're going this way, you're going this fast, and you're going in this direction at this point in space and at this time. So imagine yourself as like a little beetle, and you're sitting in the pond, and where are you going to go in space? That's kind of what that's showing. This is showing, yeah, this is the streamline. I think is a time slice. I always mix these two up. We never use these terms. We just say spatial and time distribution. So let me. She's going to be using this terminology throughout the notes. So let's make sure. Yeah. Okay. Streamline is a snapshot at some fixed time. Okay. So if you fix time and you only think about space, this is where something is going to flow throughout the. It's going to be. This is going to be a cogent trajectory. Because if you think about it, if I determine the velocity at every single point in space in like a river, when you're here, you're going to be moving this way. When you're here, you're going to be moving this way. That defines a trajectory of where you will actually move in that water. If you want to consider how it's going to change over time, you use this description. You can see it changes over time. So, okay, those are just ways to visualize what a well-defined velocity field actually means in terms of sitting in a fluid and how that fluid actually moves and how the particles in the fluid actually move. So yeah, this is just an example. You can see this x here is a vector. This u here is also a vector. They both have the same number of dimensions. This is velocity. This is space. T is a scalar. It's only one time. It's, how many seconds have elapsed. So this is your, let's say your x velocity, and this is your y velocity. So this is a vector. And it is not x dependent. So no matter where you are along the x-axis, the velocity is the same, but it is y dependent. In fact, the x velocity, the x component of the velocity, right? This is your total velocity. This is how fast you're moving. This is how much velocity in the y. This is how much velocity in the x. This is your total velocity, u. This is ux and uy. So the x component of the velocity depends on the spatial y of where you are. So the further you are up in y, the faster you're moving in the x direction. And in fact, this is actually the one they're using as the example, I believe, yt1. It is not. Disregard. So yeah, so you're actually solving for, yeah, so the velocity is also how, when they see dx dt, they're actually referring to, so he's saying dx dt, but I think he's actually, the x is actually the spatial position of the parcel of water, I think he's trying to say. So this is actually the velocity that the parcel will have at a given point, and this is how the parcel of water is actually going to change with time. Because here we are in the Eulerian description, so the actual the graph paper, the coordinates themselves are fixed; they don't move. The water moves; they stay the same. So that's what this x is. The x is like it's just fixed there. So this is how fast the water is going to be moving at any given spatial point that it shows up at. Just imagine like clear water, and there's like a grid of graph paper below it, and those are the coordinates. That's the x of t. Yeah, so you can actually solve for the trajectory, of course. What you do here is you solve for y. That's just a simple differential equation that you can solve. Y is b. So if the rate of change of y in time is a constant, then y is simply just equal to a linear function of time, in which that the coefficient b is going to be in front of the t. That's this, plus an initial condition. Once you have that, you can plug that into x. You can solve for, yeah, x, y, t. You simply plug in y here, and then you get this. And then once you have that in terms of time, what you can actually do is, if you're not interested in time and you actually want to make this thing here, what you want to do is actually graph the entire trajectory of the function of x and y with no time involved whatsoever. So what you'll actually do is see where the t's are here. Hold on. Yeah, see where the little t's, the times. What you do is you actually plug this into that in order to eliminate this t variable. So you'll solve this for t, solve the y for time, and then you'll plug that into each one of these t's, and then you get this parametric curve right here, which is the, whatever the hell it's called, streamline or path line. It's the spatial one. If you're interested in time, the other one, you don't solve for time, and you just kind of say solve for x and y in terms of time, right? So that's just a mathematical trick. It produces interesting visualizations, but don't worry about it if you can't follow those kind of algebraic and calculus manipulations. So, yep. The material time derivative. Okay, this is interesting physical content. Remember I said that we're not really departing from Newton's laws, and in fact, we're still assuming they're correct. They just get more complicated because we're not dealing with point particles like little dots anymore. F equals ma, the momentum's conserved. So we're interested in momentum here still. But the thing with a particle is the momentum can only change by a force acting on the particle and making the particle move. When you're talking about a fluid parcel, there are different ways that you can exert a force on this fluid parcel, and there are different ways the total net momentum of that fluid parcel can change. Imagine we got a bunch of water in here, and I jiggle the spoon. Okay, that's exerting force. That's the normal way that we're used to of a force changing a momentum. Okay, it's changing the momentum of the entire parcel. What actually happens is the spoon jiggles around, and it messes up with all the molecules, and then we add up all that momentum, and that net momentum is the actual momentum we're talking about. Like the field, whole time, blah, blah, blah. Yeah. I don't know if he's making explicit here. I don't see density. I just see velocity. Where's the momentum? All right, he is just talking about some field. Okay, set the field to momentum to make this make sense. The actual momentum is going to end up being the density rho times this velocity field we've been discussing. That's the new concept of momentum. With an ordinary particle, the way you change momentum is you exert a force on it like gravity and accelerates it. With this, that can still happen. The spoon jiggles, it's a little more complicated, but there's actually a second way that the momentum can change that doesn't require a force at all. And that is a bunch of molecules with a given momentum can actually flow out of or into this parcel. That's called ejection, and it's something unique to fluid mechanics. You don't see it in regular Newtonian mechanics. Advection, yes, that's what they call. So that's the idea of if you imagine like a cube and you say, what's the momentum of this cube? It can be changed by jiggling around molecules in the cube. It can also be changed because molecules are flowing in and out of this region of the fluid. That's a little mind-boggling, and it's kind of worth stopping here and meditating a bit on that very big difference between normal classical mechanics and fluid mechanics. It kind of drives home the fact that we really are dealing with a new thing. It's actually a parcel of water, and we've mathematically kind of idealized it in a certain way that's not the same as the point particles we're used to in elementary Newtonian mechanics. So think about that for a little while. The molecules can be jiggled and move faster, but also there are constantly and all the time molecules flowing in and out, and they have different momentum. So if a lot of fast ones leave and a lot of slow ones come in, the net momentum goes down and vice versa the other way around. So keep that in mind, and that is the reason for this term here. This funny little upside down delta essentially means the change in space in all directions. So the idea is if at the boundaries here, if a lot of them are flowing out this way, they get faster this way, faster that way. That's called divergence. You know what? Let me motivate this a little bit. Yeah. So we have this thing here, and it acts on a field x of t, whatever. Okay. So if this thing is positive, it's called divergence. If this thing is positive, you essentially have a source, stuff flowing outwards, like that, right? So stuff coming outwards. We're assuming that no new fluid is being added or leaving the actual entire glass. But were you to actually have like a geyser and adding fluid, that would create divergence, or like a sink where it's leaving, like going down a drain, that would be negative divergence. So the idea here is net momentum coming in or going out? That's the divergence term. Transport, yeah. Yes, so this is this field. He's saying just kind of a general field because he's being good and rigorous. He's doing this the right way. But for sake of concreteness, imagine that field's the momentum field. So that's how the momentum would change in time. That's like the normal force. If someone exerts a force like the spoon or whatever on the fluid, let's say wind in the ocean is causing waves. That's this time derivative here. So that's the momentum changing with time because the molecules are actually being perturbed. This other term here is the advective term. That is only changing the net momentum of a parcel because molecules are leaving and entering and they have different momentums. So the momentum can change that way too. But you can generalize that to any field at all. But momentum is going to be what we start with, I believe, in these lines. So let's stick with that. Conservation of mass. Yeah, so this is something that comes up all the time in physics. Anytime you have a conservation law, differentially, you can describe it this way. The idea is if you have some sort of volume like this, and you have some sort of stuff in there, this is cool. It can be anything, right? It can be electric current, it can be heat, it can be momentum in this case. The idea is I'm going to put it in the integral form implicitly because it's much more intuitive this way. But the idea is that the amount of stuff in there, if it changes over time, this term, that means that if, for example, the temperature goes down by like 3 degrees, that means this many joules of heat has left. So any change in the stuff that's actually contained in that volume over time will also have to show up if there's like little border guards there and they're measuring. They'll have to be able to tally up all that stuff actually left through whatever volume we're talking about. This is the idea of local conservation. I think he's talking about mass, local conservation of mass. The idea is mass can't disappear or appear, but the local conservation is stronger than that. It's not just saying mass can't appear or disappear, because theoretically you can have mass appear and then like 20 kilo weight disappears over here, and then 5 hours later it appears over here. Is that violating conservation of mass? Globally, not really, but locally, we're actually going to be more strict. We're going to say, no. It's not allowed to appear and compensate by appearing later. We say if it disappears at all, it has to do so locally. It has to actually, the mass system leave a region. It can't just appear and disappear. So, and that's kind of this idea of a field. And fluid mechanics is a field equation. So local conservation is going to show up here all the time. So that's, I'm not going to talk about the concept of field in physics. But the idea is, let's say you have two electrons, right? And we know in electrostatics, this electron exerts a Coulomb force on this electron. How fast does that force propagate? It's the same as in water. If I make a ripple here, how fast do the ripples go out? Whatever speed it is, if a ripple starts here and it propagates to here, it has to touch every single point in space continuously in between. That's the idea of locality. And when quantities are locally conserved, they have to respect that. That's what this equation is saying in words and concepts. So even if you don't know vector calculus, you now pretty much understand what this means. Yeah, this is just basically adding up all the mass in a region. And we're saying we don't want it to change unless it explicitly flows out, and we can account for it in tally. Yeah, so you guys are interested in the what this notation actually means. This is the amount of mass in the region and changing in time. So if I start with this much mass and I wait 10 seconds, does it go up? Does it go down the mass? That's what this is. This is the change of density added up over the entire volume. It's the same as this because density is literally just the amount of mass per volume. So the amount of mass per volume added up over the whole volume is just mass, right? And then this guy here is he's just kind of, yeah, so this is the amount going out the sides, the density plus the density times the velocity, which is the momentum. So this is how much momentum is actually leaving. This is S is the boundary of the imaginary volume of water we're talking about, and you're just adding up the amount of momentum that is crossing that imaginary boundary. And he's saying that that's equal to this in a differential form, and that has to equal the amount of stuff that changes in there. So if you're interested in the vector calculus, that's what it says. If you're interested in the concepts, it's just conservation of mass, local conservation of mass. Incompressible fluids. So this goes back to the divergence thing I kind of talked about before. In an incompressible fluid, what that actually means is that there's no divergence. So were the fluid not compressible, that is, if you don't know, remember I was talking about rubber bands and how they can flex. The velocity field would not have zero divergence. That is, I can take like a rubber band and I can stretch it a bit, and then it's kind of less dense over here than it is over here. The idea of an incompressible fluid is that if you have a velocity flow, if you have the fluid flowing along, it's not allowed to be flowing a lot faster here than it is here. Because if it's flowing a lot faster here than it is here, then you basically are changing density over time. The idea is there's no sources or sinks. Imagine a source of water like a spring or a sink, water going down the drain. But obviously we're not adding or leaving water. So think about it like a density sink, basically. The idea is that an incompressible fluid, that is you push on as much as you want and the volume won't change, including infinite little regions of it. So at any point, no matter how small, if you press on it, the volume won't change. They have no divergence. That's the vector calculus way of putting that. Note that they can have vorticity, but they can't have divergence. And this is the place actually where the mathematics of this is actually identical to electrical and magnetic fields. So a magnetic field actually doesn't have any divergence either. But of course, the math is the same, but the physics are very different because we're referring to different objects. And of course, U here is the velocity. So the velocity is not allowed to diverge. Requirement that P. Right. So this is generally conservation of mass here. That is the change of the density over time. Density actually has to flow out. And what we're saying here is that in an incompressible fluid, it's even more restrictive. That is, the divergence of the velocity actually is zero. So in that case, the density is just kind of constant. And that's true because of the argument I actually kind of just gave you. That's why the density is going to be uniform in space. There's not going to be a more dense region over here and a less dense region of fluid over there. That's the logical consequence of that. All right. Fluid flow is incompressible. Yes, it's indeed, yes. So like sound is actually this. So in any kind of fluid, if you yell underwater and someone else can hear you underwater, it is in fact compressible because sound is essentially a region compressing here and trying to uncompress, and then that kind of propagating throughout. It's kind of a pressure wave. Okay. Yeah, this is what you do in like magnetism. You can just kind of write as a vector. This is stuff that you're really only interested in if you actually know vector calculus. But essentially, you know, like potential energy, like gravity, in a conservative field, you can write the a potential energy, and it's a function only of space. You can still do that in the case where uh, the curl is zero, but it's going to be a vector potential. Sorry, long day. Um, yeah, I mean, this is just kind of, again, this is, I don't think anyone who doesn't know vector calculus is going to be interested in this or really understand this, but you can still follow the rest of the lecture without this. Sure, sure, sure. Yeah, viscosity. Remember viscosity I was talking about before. It's this second moment here. It's how much the x velocity of a molecule over here is correlated with the y velocity of a molecule over here. Essentially, it's how like sticky something is. Yeah, internal friction force. We're assuming there is no viscosity. Again, this is a very simplified idealization of the laws of fluid mechanics, and we're going to build in complexity from there, as we always do in physics. So these are the two things we assumed before: mass conservation, and we assume that the fluid is incompressible. And with those two assumptions, the Navier-Stokes essentially reduce to blah blah blah. Where is it? Yes, there. This known as the Euler equation. Um, yeah, so I'm going to explain this, and I'm going to lecture because I'm tired. Uh, okay. Right. So this is actually kind of what I was talking about before. The momentum changes for two different reasons. Momentum flux. Kind of losing the light here. Yeah, you know what? Honestly, just because I'm losing the light, I think I'm gonna stop here. But we'll pick up from this in the next slide.